Good afternoon, everyone. Respected faculty members and my fellow mates, I would like to quickly introduce ourselves. I'm Sadia Subhan Mishti and my groupmate Abid Hussain would like to present our EEE400 final term progress report presentation on design and optimization of photonic crystal fiber-based sensor for air pollution monitoring. Next, here is the outline of our presentation. At first, I'm going to talk about background, motivation, objectives, problems and challenges in the existing system, and possible solution, proposed system, addressing complex engineering problems and activities, and so on. Next. I would like to start with background of PCF. Photonic crystal fibers are fibers with an internal periodic structure made of capillaries filled with air, combining properties of optical fibers and photonic crystals. They possess a series of unique properties. The idea of photonic crystal fibers was presented for the very first time by Ye and his team in 1978. PCF comes in three categories. Number one, photonic bandgap fiber. Number two, Holy fiber. Number three, Bragg fiber. PCF can also be used in many intelligent systems, which is the core attraction of many analysts. Next. Here comes the vital roles played by PCF. Optical fibers and PCFs are different in certain areas. For example, its feature of pliability, internal geometrical structure makes it unique in its own way. PCF-based sensors are mainly used in controlled radiation therapy, plasmonic gas or chemical sensors, etc. It is also used in biochemical sensors, bacteria identification, skin treatment, eye treatment, lasers, etc. PCF can also be doped to achieve final destination. PCFs are worldwide popular because of its unparalleled properties. Next. Literature review is done to get a crystal clear knowledge about PCF-based application, the outcome, limitation, and the possible solution to those problems of three main research papers as references have been shown in the slide. Next. After studying deeply about photonic crystal fibers, we have discovered some problems regarding PCF which should be kept in mind while working with it. I would like to mention some of them. For example, fabrication of elliptical air holes and selectively filled core makes the construction of PCF more complex. Lack of precise control of waveguide parameters and narrow transmission spectral band for maintaining the band gap effect are the principal restriction of photonic crystal fiber. Lesser the diameter or pitch between the air holes make the fabrication more complicated and very costly. Maximum papers that have been reported previously do not focus on gas and chemicals that have low refractive indices. Now I would like to discuss about the objectives of this proposed system. Modifying the internal geometrical structure of PCF for simplifying the fabrication method, checking performance parameters, varying wavelength and diameter of air cavities in core and cladding of the PCF, determining the perfect values of the geometrical parameters for high sensitivity responses and low confinement loss. Next. This is the system that we are proposing for the design for the practical realization of the PCF sensor. An experimental framework is portrayed in this slide. An optical tunable source is required to pass the light through the PCF to have the interaction with the chemicals. This source can be broadband or supercontinuum. This light is passed to a polarizer and a polarizer controller to have a linearly polarized light. This light can even enter into a single mode fiber. Single mode fiber provides the opportunity to receive the light and take it into the PCF. On the other hand, there will be gases and chemicals that are to be sensed, which are required to pass through a mass flow controller. Mass flow controller secures and controls the flow of those gases and chemicals and lets them enter into the inlet. As we have an internal analyte flow channel in the core region of the fiber, we need a C-type fiber. C-type fiber serves as a gas or chemical inlet and helps analyte to flow into the core channel of the PCF. Another C-type fiber is needed to serve as an outlet and extract out the analyte from the PCF. Then we'll have another SMF that can receive the light from the PCF after interacting with the chemicals and pass it to an optical spectrometer or optical spectrum analyzer. Optical spectrum analyzer can be utilized to sense the waveforms via a computer. Next. As we can see, a cross-sectional view of proposed PCF is shown in the slide, where we have used 6 layers of hexagonal shaped ring with a constant diameter of air holes that is D4 in the cladding. The extended view of 4 has been shown as well, where we can see we have used 3 diameters, that is D1, D2, and D3. As we know, the size of hole-to-hole space is known as pitch. Pitch is also denoted as lambda. A perfectly matte layer of 1 micrometer is being used in the proposed design, which helps to absorb light and prevents the light to get reflected back into the core. Here in the right side of the slide, there is a table where given some important gases absorption wavelength. Next. These are the following equations we have used for calculating relative sensitivity and confinement loss. Next. Now, I would like to mention about addressing the complex engineering problems and activities based on our project. For problem 1, depth of knowledge required. For analyzing a 14 crystal fibers, we had to gain a vast knowledge about COMSOL software and the characteristics about optical fiber. For problem 2, range of conflicting requirements. Requirements are conflicting, all conveniences are available, but complications while reducing the diameter of a core should be minimized. For problem 3, depth of analysis required. There is no exclusive solution. Multiple design is available, but choosing the relevant design is a tough choice for which analysis is very necessary. Familiarity of issues. Electrical engineers are not frequently connected to photonic crystal fiber issues, so the project rarely comes across such issues. For problem 5, extent of applicable codes. MATLAB codes have been used for graphical representation of relativity sensitivity and confinement loss for this project. For problem 6, extent of stakeholder involvement. The project involves diverse groups for stakeholders with widely varying needs. For problem 7, interdependence. Our project requires a numerous subsystems such as optical tunable source, single mode fiber, mass flow controller, polarizer, and polarizer controller, and etc. For activities 1, next. For activities 1, range of resources, it is necessary to involve equipment and information for analyzing and implementation of the project. For activities 2, level of interaction, reducing diameter of the air holes in the core would add more complexity in fabrication, but if we can overcome this problem, this project would be able to interact with wide range. For activities 3, innovation, the project involves innovative ideas of engineering about designing the core, which gives a better value as required, which eventually degrades the cost as the project is more sustainable. For activities 4, consequences to a society and environment. Implementation of this design successfully will have a great impact on environment and air pollution monitoring in future. For activities 5, familiarity, the project involves a new unfamiliar area for electrical engineers. Next. I would also like to discuss about the impact of the project on environment and its sustainability. Air pollution in Bangladesh is due to increased poisonous gases. For example, acetylene, methane, carbon dioxide, carbon monoxide, sulfur dioxide, and etc. from the industries without proper ventilation, and it is released in the air openly. PCs are more sustainable to natural calamities than any other material comparatively. It is shown that it works for around 25 years with slight maintenance, which actually degrades the cost for repair and maintenance sector. PCF doesn't produce thermal waste. As a result, energy is saved and lasts long. And moreover, it is sustainable because it is made up of silicon dioxide, which is the second most ample element on Earth. Now, I would like to give the floor to Abid for carrying out rest of the presentation. Thank you.
Thank you, Saria. So as you can see, we have performed simulation and analysis via COMSOL multiphysics to verify the sensing capabilities of our proposed sensor. In figure 4, we can see the relative sensitivity of benzene plot against wavelength ranging from 1 to 1.8 micrometer. In figure 4b, we can see the confinement loss of benzene against wavelength ranging same as before. As the wavelength increase, our sensitivity also increases. I would like to also mention the maximum relative sensitivity of benzene is about 82.75% with a low confinement loss of 3.389 into 10 to the power minus 14 dB per meter. And in figure 5a, the relative sensitivity of methane plot against wavelength ranging from 1 to 1.8 micrometer. In figure 5b, we can see the confinement loss of methane against same wavelength. It is shown that the relative sensitivity of methane is about 71.13% with a low confinement loss of 7.099 into 10 to the power minus 11 dB per meter. And lastly, here is the figure in 6a and b shown the relative sensitivity and confinement loss for ethanol, which is we have achieved 81.85% sensitivity and a low confinement loss of 7.239 into 10 to the power minus 14 dB per meter. Now, in the case of real-life fabrication of PCF sensor, it is not possible to achieve 100% accuracy in all parameters due to natural cause and human errors. Deficiency will occur inevitably. So, we have performed variation in analyzed channel radius R1, R2, R3, and R4. Run simulation and analyze to inspect in the chains of relative sensitivity and confinement loss. As we can say here, as we can say before, R1, R2, R3 represent the core radius, and R4 represent the cladding radius. Here in figure 7, we have seen the result of relative sensitivity of benzene shifts owing to variation of radius R1. We have noticed that by increasing the radius from 0.61 to 0.65 micrometer, it gives a better relative sensitivity, which is 82.75%, and a low confinement loss. In figure 8, we have seen that The result of relative sensitivity and conformal loss of benzene shifts owing to variation of radius R2, another core radius changing from 0.31 to 0.35 micrometer. We have got better result for 0.35 micrometer. Now in figure 9, we have seen the result of relative sensitivity and conformal loss of benzene with variation of radius R3, which is also a core radius changing from 0.11 to 0.15 micrometer. We have got better result for radius 0.15 micrometer. Now in figure 10, the result of relative sensitivity and conformal loss of benzene with variation of radius R4, which is the cladding radius, changing from 0.48 to 0.52, have been shown in this graph. Now for the methane and ethanol from figure 11 to 18, we have done the same analysis by changing the core and cladding radius and plotting the relative sensitivity and conformal loss graphs. For core radius R1 0.65 micrometer, R2 0.35 micrometer, R3 0.15 micrometer gives the best relative sensitivity of 71.13% for methane and 81.85% for ethanol, with the lowest conformal loss. Moreover, it can be shown that increasing the diameter of air holes in the microstructure core and decreasing the size of hole-to-hole space, the relative sensitivity is enhanced. In addition, the conformal loss is reduced by increasing the value of diameter of the air holes in the cladding. I would like to also highlight that when we are changing a single radius, we have to keep all other parameters constant. In this slide, a comparison table of proposed PCF for benzene, methane, and ethanol with 9 other references are shown. From here, we can see that our proposed photonic crystal fiber gives us the better relative sensitivity and conformal loss for ethanol, methane, and benzene compared to others. So now, if we look onto the limitation, then conformal loss limits the photonic crystal fiber propagation length. Then higher dispersion of in PCF limits the rate of data transmission. Fabrication of elliptical air holes is more complex compared to circular. Also, fabrication complexity increases the proportion to decrease in core air hole diameters. Lastly, practical implementation of such fiber engages a lot of money. Now the future scope of this project is the structure of this PCF can be more simplified so that it can easily be fabricated. For PCF based gas sensor, core region is very important because generally gas and chemicals are flow through the core. As a result, you need to make a suitable core structure to absorb the light as much as possible. The propagation loss need to control, which is important for the practical realization. Otherwise, light will immediately vanish after launching the light on end of the fiber. As a result, it will not able to generate a measurable signal at the output end. Selective gas infertilization is required in the most of the reported PCF-based gas sensors. This is another challenge issue for practical realization. Its alternative solution could be external gas sensing approach. Now I would like to sum up this presentation with this slide. We have discussed the optical properties of PCF sensors, PCF and working principle of PCF based gas sensor. A hexagonal shaped air cladding with circular shaped analyte core photonic crystal fiber gas and chemical sensor is designed in this presentation for gas and chemical sensing purpose. The sensor displayed maximum relative sensitivity of 82.75% for benzene, 71.13% for methane, and 81.85% for ethanol, with the lowest conformal loss. According to the literature review, we have seen that the relative sensitivity and conformal loss of methane, benzene, and ethanol gives a better result than any other design so far. We are very much hopeful with the design and result that it would play a great role for air pollution monitoring in future. These are the selected references that we have used for designing and for this presentation. Thank you.